Okay, hi folks. This is activity 3 in lab 5 and it's very similar to activity 2. The geometry looks different. However, I will be doing it in a relatively, you know, in a different way than how I did activity 2. Now, uh, first of all, as soon as you see this structure, you have to realize that it must be done, and there are no ifs and buts, but by beam elements. So do not model this thing with 3D solid element. Okay. The other thing is that these ends are clamped, I believe. Points A and E are clamped, and then the middle point is being pushed down by some amount, and also that horizontal rod BH is being twisted right at the middle point by a certain number of degrees. Okay. Now, you have to use as many planes of symmetry that are applicable, and in this particular case, it's obvious that X, Z is a plane of symmetry, and what that means is that you create only half of the model. For example, let's say we do the front piece, like this piece, okay, and then at the middle point, you have to impose the constraints for the symmetry, restraints for the symmetry, actually, and because this point is in the xz plane. It does not move in y, and rotations are exactly opposite. In other words, doesn't rotate about z, doesn't rotate about x. Okay, so here's what I'm going to do. These problems can be done in many different ways. So on purpose, so that it's different from how number 2 was done, I'm going to create a sketch which has this entire piece in it. In other words, EFGH. So EFGH is a planar sketch, and I'm going to draw it, a planar curve, and I'm going to draw it in a sketch. And then from H to this middle point, I will be using a line, and eventually I have to join this sketch that I created and the line that is going to be in this place. Eventually, I'll have to do that. Okay, so what I'm going to do is I will create a plane which is let's see now 1.5 inches away from the xz plane, and in that plane I create the sketch and then do the rest of the problem. So we go here to Catia. Immediately we save this part, file, save management, and save as. I created a folder called activity 5, lab 5, and we're going to go one level up, lab 5, activity 3, so just keep it there. Okay, so right now I'm in wireframe and surface design. If it's making you feel better, so I can go to part design, though it doesn't matter. Oops, wait a minute. Uh, Mechanical design, part design, that's what I wanted. Very good. Now, I will create a plane which is 1.5 inches away from that XZ plane. There we are, 1.5 inches. And in that plane, I will create that geometry that I just mentioned to you. In other words, this piece, okay? So on this, I will sketch. Let me see now, X goes this way, so I'll try to be consistent with the coordinate system. By the way, you can always flip these things. Okay, you can always turn this thing around, but that's okay. We'll just go the way. There we are, and we're going to put some dimensions here. For example, this is 1 inch. It will be 1 inch. This is going to be 2 inches. And that radius, the radius of the circle is, I believe, is 0.5. 0.5. Let me say OK, and we exit. There we are. Okay. Now this other point, this point over here, the different ways of doing it. If you know, let's actually try it. Okay, so we're going to draw a line, and the method for creating a line is a point and direction, and the point is this point, and the direction is, let's say, direction y, and the length, let me see now, reverse the direction on that side, and the length is 1.5, I believe, 1.5. Okay, so that puts it right at the middle plane except. Okay, very good. Now, I'm going to join these two. And I mentioned this thing, mentioned why, because if I don't join the sketch and that, when I measure at this corner point, I have duplicate nodes, one from the left, which is the line, one from the right, which is the sketch. So first thing I'm going to do is you can apply material now or you can apply material later, it doesn't matter. But in order to join, you have to be either in wireframe and surface design or in generative shape design. Since we decided that our geometries are not that complicated, we can do everything in wireframe and surface design. I'm going to go to mechanical design. Right down here, this is a cheap version of generative shape design. And there is the icon for joining. You click on that, you select the sketch, and you select that line, and they're going to get joined together, joined in the sense that you see here. And then let's apply material properties on it. I think it says steel, so I'm going to select material, steel on that part, uh, default properties in Catia. Okay, good. You can change it if you double click on this, if you're interested to change these. Oops, I forgot. This on this computer, every time I click on my material, it just system crashes. Okay, so it doesn't happen on the other laptop that I use in demonstration in the lab or on yours. So it's good that I saved. Ooh. Let's see now. Where were we? Where were we? Let's go and bring it up. Start Katia. I completely forgot that this thing crashes when I try to change material. It's okay. Then I saved. I don't know how far I saved, but we'll find out. So, okay. So start. This is the one. This last part was the one that I created. Yes. Don't double click on this. For me, you can do whatever you want. So now we're going to go to analysis and simulation, generative structure analysis. Okay. And you have to mesh it with beam elements. And because you join these things, when you click on this, the entire thing is going to get meshed. So you select that, turns yellow, that's a good sign. Why don't we make the size of this thing about 0.1? So there's going to be, I don't know, 15 elements this way, 20 elements this way, etc. But these are very robust elements, so we don't need that many. With maybe 5 or 6 elements, you can get excellent result. If you look at the mesh visualization, you can see your mesh, nothing exotic here. Let's make sure that there are no duplicate nodes. See, this corner node is node 4 when you go from this side, and it is also node 4 when you go from the other side. If you had not joined this thing, there would have been duplicate nodes here. There are ways to fix this, there are ways to handle that, but I don't want to do it. We haven't talked about it, so deactivate. Okay, good. Now let's apply the cross-sectional properties. Now notice that here, let me see now, were they different? Let's see for a second. Yeah, this one, this middle piece, the one that goes from D to H, has a different cross-sectional radius, 0.025, whereas these are 0.5. So this is, you have to take care of that. I had the same situation in activity number 2. So what I did, I said, okay, there is a way to do these separately, put properties separately on it, but I'm going to put everything first to begin with, for example, as 0.5, circular with radius 0.5, and then using the local mesh property, I can change the one over here. That's how I'm going to do that. So here is the 1D property. You click on this. When you click on this, the whole thing is going to be picked because the entire thing is joined together. Cylindrical with radius 0.5. 0.5. You say OK. And we don't need an orientation point because the circle, we can actually close it. Now, when you create the properties here, you can see it's created. Right click local mesh property. You can go and select that line and put whatever you want. You want 0.025. So this is a trick that you can use. There are other ways of doing it, obviously. Okay, so if you zoom in, you see that actually uh, this one is 0.5, this is 0.025, a lot thinner, okay? 10 times, maybe 20 times smaller. Yeah, 20 times smaller. I just want to make sure that I read this here, 0.025 versus 0.5, yeah, good. Excellent. So I didn't mean it to be that much of a difference, but anyway, it'll work. So that takes care of this. Anything that you don't want, you can hide. So for example, this one, you can say hide it, don't show it to me because it's bothering me. Now, this point is clamped, so we go and clamp it. Okay, clamp means that 3 translation and 3 rotations are fixed. This is in the plane of symmetry, okay? So you use user defined, let's uncheck all of these. This point is in the XZ plane of symmetry, so there is no displacement in direction Y, and rotation is exactly the opposite. Because this is check, rotation about Y is not check. Because these are free, rotation about those axes are in fact check. That's the way symmetry works. Now, what you want to do, again, anything you don't want, you can hide it. These things are right. You want to push this thing down, and then we want to twist it also by so many degrees. Because in Catia, to give a non-zero value, you have to give 0 value and then change it. That's what I'm going to do. I'm going to click on this. I'm going to click that point, and this point, we like to push it down, so I can say 0 in the downward direction. This is 0. And I want to twist it about the, I think it was the y-axis, so rotation about the y-axis, 0. Now I can go and check it. If I click on the enforce displacement and select this, the only two things that you can change are downward displacement and rotation. Now, if you look at this diagram, it says that yeah, downward displacement of 0.001 and 2 degrees rotation, for example, in the direction that you have. So let's go here. This one is still 0.001 because problem 1 was also the same. Activity 2 was also the same number. That's why I put this number in activity 2 still there. And this is also the same, except that I insist on doing it in the direction that's specified, which is actually negative 2 degrees. Okay. All right. Yeah. Negative 2 degrees. Let me see now. Negative 2 degrees. Yep. That's good. So let's first of all save this analysis in case things crash. File, save management, analysis, save as in that folder, analysis 1. So okay. And hopefully we didn't forget anything. I don't think we have forgotten. So let's go ahead and run it. Let's see what happens. I'm sure it's going to be okay. So look at the deflection. Apologizo. So it's going to look like that. Okay, notice that it does not come off the exit plane because we put symmetry condition on it. There's no way it's going to come out. Okay. Now, you cannot plot von Mises stress. You know that. You can only plot the axial principal stress, which is totally useless. Right there. Totally useless. These are the axial stresses, but useless. So I'm going to deactivate that because we're almost done with this problem. It says, the problem says, write down how much moment is needed in order to create that 2-degree rotation. Write it in here. It should go in there. Okay. So the way to do that is actually go ahead and create a sensor there. So you go to sensor, right click, create resultant sensor, reaction sensor. It says, okay, which one, which sensor, which restraint you want to use. This is the restraint that I want to get some information about, right there. See that? See this? And update. It says that you need this much force, very little force actually. That's because this is such a flimsy, uh, uh, you know, so uh, flimsy as far as the size is concerned. Very little force. And for moment, you go here, it says you need that much moment, 0.1 pound per inch. Now, the answer that goes in this box is not zero point 0.1 pound by inch. It is double of that because this is the moment needed for twisting this piece by 2 degrees. The other piece is also there and we use symmetry. So the number that goes in this box is actually double of that. Okay? And that takes care of this other activity. So let me stop this.